our last group of identities. These are the half-angle identities. They allow us to write out or find the value of sine or cosine or tangent of half an angle if we know something about the angle itself. Now, these are written where this is sort of solved for, in this case, let's just take a look at this first one, this sine of alpha over 2. Plus or minus the square root of 1 minus cosine alpha over 2. Now, whether it's positive or negative kind of depends on what quadrant alpha is in, because depending on what quadrant alpha is in will affect what quadrant alpha over 2 is in, right? And that will obviously affect whether sine or cosine or tangent is positive or negative. Now, a lot of books will write this identity and the one right below it as well, so that they've solved it for sine squared. So it would appear like sine squared of alpha over 2 is 1 minus cosine alpha all divided by 2. Because when you're squaring it, then you get rid of the ambiguity of the plus or minus. Not that it's not there anymore, because clearly we're just solving it for sine squared. But depending on the resource you look at, you'll see the identities written in terms of solving for sine squared or cosine squared, or just the sine or cosine function. So let's work through a problem. They want us to simplify this. They're not telling us. There's not a whole lot to go on, except that I look at this and I say, well, that looks kind of like one of those two formulas over there. This one involves a radical 2, but we've got cosines both in the top and the bottom, and here we've only got a cosine up top. The other thing, if I were to pick one of these two, it seems to look most like, which one would you say? The bottom one? Yeah, because this is a plus and not a minus. That's really the only difference, right, between the half angle for cosine and the half angle for sine. They both are written in terms of cosine of alpha. It's just that in one of them we're adding in the numerator, and the other one we're subtracting. So the thing that's really different is this is a 9 plus and this is 1 plus. But we have a 9 in both terms, so we could factor that out. And if I have a factor of 9 sitting inside this radical, what can we do?
Factor out a 3?
Yeah, this will come out as a 3.
Is there still a plus or minus in the beginning?
There is no plus or minus because they did not give us a plus or minus in the beginning. Yeah. The plus or minus really depends on if we know something about the angle itself. Like if I wanted to use a half angle identity to find sine of 15 degrees because I maybe know the exact value of sine of 30 degrees, this will tell me how to do that. And it could be plus or minus depending on, 15 degrees, that would end up being plus because it's in the first quadrant. All right, we factored out the 3. Now what?
Would it just be 3 cosine alpha over 2? Or what I guess.
So it would be, whatever this argument is over 2. Yeah. So 6x over 2. So yeah, 3 cosine of 3x. There are, the exercises we're doing right now might just seem like, well, we're doing it because it's what's in the book, or we're doing it because somebody's just asking me to. But there are times when, like if I needed to solve an equation and I wanted to know, well, where is this expression equal to 0? It'd certainly be a lot easier if I know how to use identities. Finding where this is equal to 0 would be almost trivial. It'd be very simple with the unit circle and be a lot more work in this form. For those who might be going on to take calculus, one of the things we do is like differentiate functions and integrate functions, and both of those things are much, much easier if you write it for a function that's written in this form. Like, I'm going to go infinitely easier for a function written like this compared to a function written like that. Did you ever hand up?
Yeah, how do we get from the radical to the 6x over 2?
Because we used this identity here. So what we have here is written in that form.
Oh, okay. I see.
Yep. What's that? Yeah. Yep. Oh, this one looks fun. All right, we're going to show that this stuff on the left side is equal to 2 sine of 1/2 alpha. We can sort of see where maybe the half angle identity might come into play here. The arguments inside functions on the left side are alpha. On the right side, they're 1/2 alpha. So it seems plausible that we might find a half angle identity useful. In keeping with our sort of general strategy of let's start on the side with the most business, I would suggest maybe there's more to work with on the left side. So if we start here, what opportunities do we have right now?
Without the 1 minus cosine.
Yeah, and that's, I think there's not much more we could do other than that, right? Like algebraically, that's sort of like the low-hanging fruit, at least. So if we FOIL this out, we get 1 minus 2 cosine alpha plus cosine squared alpha, and I guess alpha, not x. Don't need the parentheses. And then plus sine squared alpha. This is all underneath the radical. What now?
Set cosine squared alpha plus sine squared alpha equal to 1.
Sure, yeah. We're getting pretty good at recognizing this opportunity when it comes up, right? We know that Pythagoras tells us that that sum is equal to 1. The thing that we check, and especially once we get to working with problems in this section and the last one, is just a quick check that the arguments inside are the same. That's important. That it's cosine squared alpha and sine squared alpha. So if that's 1, then what we have in here is that can combine with this one, and we have 2 minus 2 cosine alpha. Now we're still not quite done, especially if we're definitely not done, right? Look at where we want to go. But we know it seems plausible, right? It seems like we're going to use a half angle identity somewhere. We're trying to get a sine of 1/2 alpha. So if we look at the half angle identity for sine right here, we do have a 1 minus cosine alpha over 2 inside the radical. And it seems like we're kind of circling around that type of expression. I am subtracting inside a radical, but the stuff that we're subtracting, this is over 1 instead of over 2. So let's just put in a factor of 2 on the top and the bottom. If we want it to see that factor of 2 in the bottom, we'll just throw it in as long as we don't break the rules in doing so. So we have 4 minus 4 cosine alpha over 2. What could we do next? Yeah. Now what?
Take out 2's from there. 4.
Yeah, so this factor of 4 will come out as a 2. So now we got 2 times the square root of 1 minus cosine alpha over 2.
That's the same thing as sine alpha over.
Yeah, yeah. So now we have 2 sine of alpha over 2. And of course, alpha over 2 is the same as 1/2 alpha. So we're done. I told you this one was fun, didn't I? More?
Sure.
All right. All right, we want to show that this is equal to 1. Where do we begin?
Would it be possible to take the 2 cosine squared x over 2 and to sort of reverse, put it under a radical?
Oh, yeah, yeah. You mean like use the cosine of x over 2, the half angle identity? Yeah, and then we'll just square it. Like we have cosine. So what we have is, I'm going to write something in between.
Okay.
Cosine x over 2 all squared, right? That's what cosine squared means. And this stuff right here is something we can use that half angle identity for cosine. So we got 2, and then plus or minus the square root of 1 plus cosine x all over 2, and we're squaring this. I love it when we are using a half angle identity in conjunction with the squaring because it does eliminate, especially when we're using it in this direction, where we're starting with the half angle in the function and then going to that radical form. We square it and then we eliminate whether that's a positive radical or a negative radical. When I square it, I know it's going to be positive. So what do we get in our next line? Just like algebraically.
2 times 1 plus cosine x over 2.
Yeah. Yep. And then minus cosine x. Now we can sort of see the light at the end. We're going to cancel these 2's. We get 1 plus cosine x minus cosine x, and that's 1. And we're pretty happy about that. Questions on this example? All right, well, let's try one more. This is not a proof. They just want us to derive an expression for secant alpha over 2 in terms of cosine alpha. Now, if they said just in terms of the cosine function, I would say, oh, yeah, it's 1 over cosine of alpha over 2, and I'd be done, right? But we want to write it in terms of cosine alpha. So we'll start with that step, 1 over cosine of alpha over 2. But I want to get this in terms of cosine of alpha. So I think the first thing we might do is just use that half angle identity. And it says that, so we have 1 over, the cosine of alpha over 2 is plus or minus the square root of 1 plus cosine alpha over 2. Solve that fraction inside the radical. Now what they don't say explicitly, but is always implied in these problems, is and simplify it, right? So this is horribly unsimplified. Not only do we have fractions within fractions, we've got a fraction inside a radical within a fraction, so we got a little bit of work to do. A couple of ways we could proceed, but you know, I might suggest starting by we could split up this radical over division. And now that we're dividing by a fraction, we can just write it as multiplying by the reciprocal. So we have 1 times plus or minus root 2 over the square root of 1 plus cosine alpha. And now we're kind of almost done, I guess. Really, obviously, the times 1, it doesn't matter. We can drop that factor of 1. And we can put this back into a single fraction. You could, if you want, break it up to like rationalize the denominator, but that's not really necessary, so whether you do that or not would be fine. Yeah, it's fine to end it here. Yeah.
So why couldn't, going back up, why couldn't you just change 1 plus cosine alpha, yeah, right, what's underneath the 1, yeah, that. Why couldn't you just change that to cosine alpha over 2? Is it because it wouldn't get us anywhere?
Well, that would actually be going backwards.
Oh.
Yep.
Okay.
Ken, we wanted to write it in terms of cosine alpha.
Oh, okay.
Yep. Good. That's a good question. Sometimes, you know, I always when I'm working on these types of problems. I mean, I've said that I know I repeat myself, but I always just keep thinking I got to keep my eye on the ball. Like remind myself where it is I want to go, because it can be easy to kind of feel like we're going in circles when we're working with these.